In this video, we're going to stitch together our models into one continuous model that describes the operation of a BJT in all bias regions. The model is called the Ebers-Moll model. This is a good tool to have because we can take derivatives of it and graph it, but it's too complicated for use in circuits. We'll derive the circuit analysis usable models in a later video. We can start to make this model by combining models from our cutoff, saturation, and forward active regions. These back-to-back diodes work for cutoff and saturation, and we add in this current source to represent forward active. However, this looks a little lopsided. The model contains an asymmetry where the forward current in this lower diode can trigger a current source, but the reverse current can't. That lopsidedness represents a hole in our model. The BJT is a somewhat symmetric device, right? It goes NPN, so you can spell that backwards and forwards. So the active behavior we described has a reverse active analog, where the collector injects carriers into the base and the emitter absorbs them. Reverse active conduction works very poorly because of the reverse doping profile, and it's difficult to induce by lab, even by accident, so we rarely consider it in our circuit models. However, it helps us paint a complete picture of the carrier flows in the BJT. Now the forward diode and the current source describe forward active behavior, so these two elements capture forward active. The reverse diode and current source capture reverse active behavior. And we can still rely on the pair of diodes to capture both cutoff and saturation, because in cutoff, IR and IF are 0, which also turns off these sources. And in saturation, IR and IF are big, which means that we're just going to get some sort of like linear subtraction from both IR and IF from the current sources. And that'll change like our effective IES or something, but it doesn't undermine the fact that we'll still get exponentials. We can use this circuit diagram to make equations for the collector and the emitter current. I've substituted the expressions for forward and reverse current in these equations as indicated on the top of this slide. So we can see that the collector current is just alpha F times IF minus IR, which, if you look at the collector, is alpha F IF minus IR, which is flowing in the opposite direction. And similarly, the emitter current is IF minus alpha R IR. So emitter current is IF minus alpha R IR. And alpha R is a new parameter that describes carrier recombination and reverse active that is similar to alpha F. Because the recombination rate in the base is constant, we know that alpha F times IES has to be the same as alpha R times ICS. We define this quantity as IS, which lets us simplify the notation that we use for the BJT. Substituting the useful fact expression that we just derived into our first cut at Ebers-Moll equations gives us our final Ebers-Moll model, which is written in terms of IS, alpha R, and alpha F. There are lots of useful things to notice about this, but one is that both the collector and the emitter voltage current depend on both VBE and VBC. That means that the IV curves are likely to be somewhat complicated. We'll tackle that complexity by rendering the IV curves in a few different ways. On the left we see a picture of base current versus base emitter voltage, and this just behaves like a diode that matches our Ebers-Moll model, which has a diode connected between the base and the emitter. Changing the collector emitter voltage won't affect this much. The collector current is linear in the base current, so it's also an exponential when plotted against VBE. This curve is the same shape as the base current, but it's been multiplied by a large coefficient, because alpha of the emitter current comes from the collector, while 1 minus alpha of it comes from the base. And at very high current levels, the IC curve will bend to horizontal lines as the BJT saturates. However, it's difficult to represent that behavior on a plot with VBE on the x-axis because the change in IC is so rapid, the exponential behavior is fast. As a result, it's common to plot IC versus VCE parametrized in VBE, where parametrized means drawing multiple curves at different VBE levels. The left side of this plot shows an exponential increase in IC current as VCE increases, because it's representing the saturation region, where the collector current is controlled by a diode. The right side of this plot shows the current remaining stable as VCE changes, which is consistent with our forward active model. In the forward active model, the current source prevents changes in the collector voltage from affecting the current at the base or the emitter. The level at which the current flattens out is set by VBE, which is also consistent with this model because IE here is determined by our base emitter voltage. This region of the plot that we have highlighted for our forward active circuit is actually a beautiful part of the plot because it's key to transistor operation. Changing the base voltage will change the collector current, but changing the collector voltage won't. So we've transferred the signal on the base into current at the collector. As a result, we'll almost always seek to operate our transistors in the forward active region when we're doing analog design. So they'll be over here and not over here in the saturation region. By the way, one thing to note about the saturation region is you can observe that it happens when the collector is low and the base is high, which is consistent with how we defined the diode relationships that specify the saturation region. So in summary, the Ebers-Moll model is a continuous model that represents all regions of BJT operation. You can use the Ebers-Moll model to draw BJT IV curves, which are usually VCE IC curves that are parameterized in VBE. And we're going to add one more detail to our model, then use it to calculate small signal models in the near future.